Hey, Bob. Ted and Ivan are still helping people in the other room. So Ivan will close that one and will join us with some of the participants which are already in the other room. So yeah, just wanted to let you know so you can start anytime you want.
That's good. I'm losing my voice, so I'll just drink tea for a while.
Oh, okay, sure. Well, Ivan just closed the other room and people are, I guess, either wandering around or will join us very soon. Yeah, I see they are joining us.
Ted, do you think it's possible for you to share the notebook one on your computer, because yours is a bit faster than mine in terms of running time?
Yeah, sure.
Do you think we're mostly, I guess we're mostly back, huh?
So yeah.
What we'll do, Ted, is I'll share while I just make some comments. And then when it comes to running, then we can let you run it, okay?
Yep, sounds good.
So I hope everybody has, or everybody who's tried has a copy of the Docker version on their system. And so this time is for you guys to run some of the tutorial modules. I can maybe start by pointing you to the description of them and say a few words about them. So the things we prepared for tutorials for today are these three. The first one focuses on how you would set up a notebook to build models from your own images. And I thought I would go through that with you together. If you're not that interested in that and you want to go ahead and run the notebooks or look at the notebooks in modules 2 or 3, please feel free to do that. But what I'm going to do is share the notebook for module 1 and kind of talk a little bit about what is in there. So here's an example of a notebook for running CellOrganizer. As you might imagine, what it starts out with a bunch of imports. The thing of most relevance here is, can everybody see my screen and cursor? Or can anyone see my screen and cursor? Is this all being shared properly? Okay. Is to import the module, the modules we need, which are image test LML and SLMelt info. Then we're going to set up the file specifications. In this case, this little section right here is just, saying where should the results go, and then making a folder within the results with the name of the module. So all of this is just kind of housekeeping. I'm happy to answer questions about it if need be, but that's just setting things so that we're changing to the directory within the results folder for this particular module. And then, so this is the important part starting here. I mean, so this is important. So as I mentioned, the options is a directory and the variables within it correspond to the options in the MATLAB version, except that where in the MATLAB version, this would be a structure and substructures and so on. Here, these are just individual, you spell out the individual structure and substructure and so on. So in MATLAB, this would be, model.name equals module name. In this case, we're setting that entry into the dictionary. All right. So options for how much we want it to report, and options, if we're making multiple models and we want to set a particular ID for this model. Here's another thing I mentioned earlier, which is we're choosing in this case, just for speed of running it, to downsample the images before running them, and also to make them roughly isotropic, because these original images, here are the pixel sizes. And so this is getting them close to being square pixel or cubic pixels. And so these things are all here, and they're not being used for this particular model. Put them there, we're going to use them later. And they're all commented out. Okay, so now we're going to tell the system, set the option for what kind of model do we want to build. That's the train flag. Framework, as you remember, is the combination of a cell and nuclear membrane. What are we going to use for that? We're going to use for the cell model, we're going to use class cell membrane and type ratio model. Ratio model is a model that is conditional on the nuclear model, and it learns the distribution of the distances of the cell membrane from the nuclear membrane as ratios. So at each point around the compass, it is learning what's the distance, the ratio between the distance from the center of the nucleus to the edge of the nucleus at that point and to the corresponding edge on the cell. So that ratio is what it's learning. And this is saying, okay, what kind of model do you want to learn for the nuclear membrane? That is fitting what is a cylindrical surface. So what it does is it takes each slice of the nuclear shape and fits a set of a polygon. And so it fits, it puts a polygon in each slice, in each slice. And then that's the nuclear model. And then it's learning the distribution of over those cylinders for this particular case. Okay. That's all we need for this particular model. It's a very simple one. And then the other thing we need, and this is what we're going to spend a little bit of time on, the subject of this one is, what do I do if I have my own images? As I mentioned, one of the possibilities is that I have files with one cell and one channel in them, in which case there needs to be some way I can distinguish each cell from each other and each channel from each other. So what this is doing, these are all commented out because we're going to not use this model right now. But if you were to use this approach where you have files with one fluorescence channel and one cell in each file, you would uncomment all of this stuff, specify where they are, and then initialize these two to empty, these, and then these two lists. And then this is saying in this directory, the files with each cell have this name, and you'll notice it says channel 1, time point 1 here. Okay, so that says, now find me all the cells that have that match that pattern. Okay, so in this directory, look at this pattern, find them all, and for each of them, append them onto the cell images path list. All right, and then do the same thing, and notice the difference here. This says channel 0, and stick that into the DNA images. So what this is going to do is to say, give me a list of all of the cells, all the files, I'm sorry, that match this pattern. So these are going to be one followed by anything, but then separated by an underscore, followed by a single digit, separated by an underscore, and then the ones that say channel 0, and then another list over here for the ones that say channel 1. A critical thing is those both need to be in the same order. So if this is cell 10, you want to have cell 10 matched to it. So these two lists have to be in the same order. So this sorts them both logically, because when you do the reading of the directory, it may just be, depending on your operating system, it may be in arbitrary order that they are in the folder. So it sorts them. And then what these lines are doing is it says, again, just for quickness, just take 3 of those. We're going to take the first 3 images that are in that in those 2 lists. Questions about that so far? All right. Then we can do the same thing if we have multiple cells and a single channel. So in that case, it's gonna look very much the same, except recognize that these need to be, we need to have an appropriate mask for each of them. Okay, so there's this, what this is doing is saying that there's a corresponding mask for each of these that tells you where the image is, and that is what you use to isolate that cell in that image. So it's basically the same as before, except that now we have this extra folder, extra list for the masks, and the masks get stored in this in the options block in an entry called masks. Okay. And then again, sort and pull out just the ones we need. Now, the most useful one is, and the most common one, is that you have files with multiple channels, all your fluorescence channels in the same file, and multiple cells. And so in this case, your images need to be OME TIFF files that contain regions of interest. Okay. And we're going to talk on Friday. Ted's going to show you how to take multi-cell images and segment them and write them out as OME TIFF files. Okay. And so these, you notice, are uncommented. We don't need any masks. And again, we specify this is a different directory where those images are. We just read them. Now, here's the thing. These are multiple channel images. So we need to tell CellOrganizer what channel to use. And so what this does is it says, find me all the files, right? And for each of them, append its name plus colon and the channel number to use, and colon and the time point. Now, there's only one time point in these images, but you have to tell it. Actually, these might have more than one time point, I'm not sure. But we're telling it use time point, just the first time point. Okay, so that builds up the list again of our files. We sort it, and then we're ready to run image test LML. That's very straightforward. We just call it, tell it there are 3D images, path for the nuclei defining images, path for the cell defining images. Here is where the path to the protein images would go, and then our options block. Okay, and that would run it and create a model. So maybe Ted, if you want to, let me first stop and see if there are any questions about anything we just talked about. Yes, somebody pointed out the notebooks are all in the local directory. I should have opened this one for you so you could see that. And I'm going to stop sharing, Ted, and then maybe if you want to start running. and sharing.
Okay. So do we want to start running like an example from module
Just-
one?
Let's just run this one. Run module one.
Okay. So yeah, this is
Yeah.
module one, what Bob was talking about. First, we initialize our general
Yeah, so
option.
just go ahead and run it, Ted. You run all from, go to cell, run all, and just run the whole thing. No, we already had, just run the one that, don't change anything, just run the one that, okay, I realized that I had, okay, yeah, you can uncomment one of the options, one of the ways of reading. You're absolutely right. I forgot I had done that already to mine. And then just run all, right?
Are we going to show them the 3 different ways or just pick one of the ways?
No, just run this, run all on this now that you've set the first way.
Okay.
Robert, sorry, quick question. Where is the source code is located?
But you got to run all, Ted, not just the last line, right? You have to run them all, didn't you?
No, because these are the different ways to do it.
But did you run the one that you're using?
Yep.
Okay.
This one's being run.
Sorry, go ahead. There was a question.
Yeah, Robert, where is the source code for the module one located? Is it like, are we gonna get the link to
It's
it?
in local. If you've got Docker running, it's in local, notebooks, workshop demos, and then they're all there.
Yeah, let me see that. I missed that part because my connection was really bad.
Okay, so just once you have Docker running, go to local, and then inside of local, there is notebooks, and then in notebooks, there's workshop demos, and then each of the notebooks are in there. Find them? Now, Ted just switched to his terminal, and this is showing what is being generated by CellOrganizer as it learns, as it runs. Okay.
Yep. So this is what it's loading in. And then it goes through validating input arguments. Do you want me to show all this, or do you want me to show the output?
Yeah, you can just scroll through it and
Okay.
and then people can see. It's just telling you everything that it's interpreted from the options that you set. And then it starts. And in this case, there were 3 images in that set. So it parses the input argument list, puts them into internal lists in CellOrganizer, and then starts processing each of them, right? So it just processed the first cell. Notice that it's channel 0 and channel 1 for cell number 10, and then it built the models for those, builds the model for the next cell, builds the model for the next cell, and then it saves everything into the model. Okay, and at one point in there it says, I didn't find a protein model, so I'm not saving anything for the protein model because we didn't ask it to. All right. Then if we go back to the workshop, to the notebook, it should have said, yep, I'm done, right?
Yep. And then you can find your outputs if you go back to your local folder, and then there suddenly appears a results folder. You can go in and it's by the module number. So it was module 1, click on module 1, and then you have the model file.
Right. And the log is a copy of everything we just looked at. And if you look, and then in, which is can be useful if you're going to do any working with the model itself, like we were talking about earlier, trying to build your own statistical model on top of it. You go back to the back one and go to the param folder. In there are the parameters for each of the cells. Okay. So if you these are the parameters that were learned from each of the individual cells. So param1 is cell, whatever the first cell was, and so on. And then it puts them together into the model. All right. Questions about any of that? So
Yeah, Robert, I have a question. Sorry
yeah.
about that. Uh, kind of a little, I understand the whole pretty much idea here, but I'm having a difficulty to get to the actual module one. I just optimized the actual Docker on my Mac OS.
Mhm.
And I was able to get things that on Google Doc, where you get chmod, Docker run on Mac OS, with actual removing, with going all this, and it tells that the container size probably you should be. I was able to, then I killed the command with control C. But the thing is, how do we get to the actual running the actual Docker? Running the actual CellOrganizer within, let's say, terminal?
Okay, so inside of terminal, you're gonna run the Docker container. Okay, Ted, do you want to share that? Share a new term. Share, I guess, the same terminal that you had open that ran previously. All right, you know what? I can share mine.
Sorry, it took a little bit of a while to kind of upload the Docker, because it looks like
yeah. I
several
totally
gigabytes.
get it. Let me just what I'll do is I'll paste into the
chat
the command.
Mhm.
And what you're going to notice there, this is in the install instructions, by the way, but let me just put it in here. Chat. Now, what you'll notice is this one's a little different than what's in the instructions, because I have a smaller machine, and so I'm only running with one CPU
Right.
for Docker. Okay. And all that does is it runs, and it's all this is doing is telling you, what folder do you want to connect to this container? That's this local folder that you end up seeing. And tells me run that particular container. Okay, that's what you would do in terminal, and then terminal would show you all the output. Now, apparently somebody on Windows says they didn't get any output, but it worked. So I guess maybe in Windows, I don't know what that means. I don't know why that happens, but I guess if it runs, you also have the log. So everything that was in the terminal is in the log. So you could always take a look at that in order to figure out if there's any messages that are, if something doesn't work and there's something in the log, and then you just look at the log to figure out what happened.
So Robert, correct me if I'm wrong. So every time I would wanted to run the CellOrganizer, I would need to do that prompt, Docker run.
No, you can have it running and have multiple notebooks open and be running multiple things. Right. So
yeah, but where are the
theoretically you would just
yeah.
you would do the Docker run once, and then open up your and then okay, you have to copy when you do the Docker run. It will give you
the URL. I copied that URL. Yeah, and then
URL. So that's now your main home base, and you can run any of the notebooks out of that.
Oh, so it gives me a local with a 0. So basically, I'm in that. It gives me kind of like an IP address with a local number of notebooks. So that's where I'm working in, and that's my working environment now. That's what it is.
Yeah, did you pull? There should be a link in a notebook in there to pull all the other notebooks. Did you pull that already?
It says a server arrow at the bottom of the message. So I see the actual CellOrganizer logo with the files running in clusters. There is no terminals, no running, there's cluster. Because I actually kind of killed the command after it was running for a little bit, but I thought it was...
you're going to have to, then that's dead. So you're going to, if you killed the command in the terminal, then you're going to have to close that window, that browser window,
And rerun it again?
Restart Docker and then reconnect to the URL, and then you should see everything. If you, and then once you do that, if you haven't already, you want to run that notebook that downloads all the files. Okay. It
Where's that?
downloads.
Yeah, where's that notebook that
That
connects?
will be in the, once you go to the URL,
Okay,
at that page, and then you will see in there a notebook that is called download files that will
yeah, I would
download.
copy, so correct me if I'm wrong, sorry, Robert. So I would just copy and paste the same URL that I,
Not the same, it'll be a different URL this time.
also I gotta rerun the whole thing again, that's what you're saying?
No, hold on. Close your browser. You've already Control-C'd out of the Docker. So
Right.
run the Docker command. It will give you a new URL.
Okay, yeah, got it. Mhm.
Copy that into the browser, and then you will get the CellOrganizer Docker window or notebook window. And what you should see is a local folder. Here, let me just share. Ted, you want to stop sharing for a minute and let me, so everybody can see what this looks like.
All right, so I just rerun it and it gave me a new container URL. I
Correct.
believe. So HTTP, so it's open source, and then there's a token there with a the Docker container ID. So I'm just going to recopy that URL. So is that the process every time I would want to run it? Or so once I've done this, this is my local kind of a, this is my kind of a niche, so to speak, in there. So I want to make sure I understand the just you know.
So what I'm saying is that once you run Docker, unless you kill it, it will continue to run and you can connect to it.
Mhm.
Okay? And then once, if you kill it, then it will not, then you have to disconnect and restart, right? So this is what you should see. Can everybody, I hope everybody can see that.
Yeah, that's what I saw earlier, but now I
Right.
close
So
it.
you want, once you, that will be, once you've restarted Docker and copied the URL in, you'll get this page. And if you haven't done it previously, you want to execute this notebook. All right, now I've already done it. So if I go into local, I'll see all of these files.
Okay.
All
I
right.
think I didn't restart the Docker. That might be an issue.
Okay, yeah, if you have a connection to a dead server, nothing will work, right? This page won't work if there's not a corresponding Docker server running it.
Mhm.
Okay.
Yeah, now I see Fernet. Someone posted something. Murphy Lab Cell running. Is that the one? I see it in a Docker now.
Yeah, you should. Do you see this page? Is everybody seeing?
Hold on. No, I just reopened the Docker. Now I see in the actual containers in the Docker because I couldn't see that before. So I'm recopying this. Oh, okay. Right, now I got it. Robert, thank you so much. So I think the issue was I did not restart the Docker. I think I remember there was the actual step that you have to shut down the Docker and restart it in order to refresh
Exactly.
it.
So you should see this right now.
Yeah, I do. Yeah.
And this is what you would run to copy all the files that are shown here. Because right now, this should be empty for you, right? This local directory should be empty.
Yeah.
Unless you've already run the notebook.
No, I haven't.
Okay. All right. Other questions about any of that?
Thank you.
From anyone? Well, we'll take a moment here. Okay. So let's go back to our, where do I have it? Here we go. Okay. So Once we've run this with this particular model, then we might decide, well, you know, I don't like that model. I want a better model. And as we talked about earlier, the best one is this for 3D is this farm RPDM. So if we want to change, we would just comment out this line and uncomment this line. And now we're saying use this farm RPM for the model. And we would do the same thing for the nuclear model, right? So we would comment out that and uncomment this. Now, there is one more thing that is needed for the swarm RPDM models. It has to know, even though you would think you could figure it out for itself, it has to know what you want to build the models for. And so in this case, we're going to build swarm models for both, if we were doing that, for both the cell and the nucleus, so we'd have to uncomment this line. If we're building a model just for the cell shape, then we would uncomment this line. I think maybe we'll make a note for the next time and see if we can figure out how to set those automatically from knowing the options, which should be possible. And then you would run it again, and then that would build that model for you. That is the one that is quite CPU intensive. Ted, I'm going to stop sharing, and if you want to start running that model, so just so people can see what the output looks like. Okay. And actually, yeah.
So do you want to from 1B, from module 1B, or?
Yeah, that's fine. I mean, you
this
guys don't have a copy of module 1B. That's just one we made this morning that is the same as module 1, but it has the changes that I just talked about. Okay, so you want to run that one?
So this will take a very long time too.
Yeah, but you can go to the, just so people can see what's happening, go to the window, the terminal window. And what you'll see, yeah, if you scroll all the way down. So it's doing the same thing where it's reading in each of the files and telling you what it's doing. And then it gets to the good part pretty soon here. And okay, so this is it reading the first cell and telling you what it's doing. The first thing it did, which is common to all of the approaches, is it finds the boundaries of the nucleus and the boundaries of the cell. That's where it says finding objects. Okay, and just as you know, for information purposes, and you can threshold on this value. You can set a minimum or maximum ratio. What it's saying is the nucleus is half of the cell, which is not unreasonable. And so it tells you that. And like I said, you could set an option that would truncate that if you're worried that some of your cells in your images maybe are partial cells, and you want to get rid of, and you want to make sure they all have the right ratio, then you could set a filter on that. So then it says fixed topology, which is filling any holes in those images. And then it now starts here where it says start to perform sparkle parameterization. That is where it is trying to find those the positions on the cell that should map to each of the vertices in the sphere, right? So we're having evenly spaced points on the sphere. And then we're trying to map those to points on the surface, on the cell shape. Okay. And so that's what it's doing here. Is it, you want to scroll up for a bit or scroll to the end?
This is them. It's still solving.
Okay, your computer's a lot faster than mine. So it's doing that now for, we just finished it for the cell shape. And now it's doing it for the nuclear shape. By the way, notice there that on the top it says final parameterization, pass quality check, Hausdorff distance is 1.2. And so that means it's there was an option that could be set to say, is it, if the distance is too big, then ignore that cell. And pretty soon it should be done with the nucleus, and then it will say, okay, I've finished cell 1, and it'll go on to cell 2. Okay. Questions about any of that, and and interpreting that? Oh, looks like it's getting there. Want to scroll up? Is it?
No, this will take quite a long time.
Okay.
Even on this computer.
Okay. Then let's talk about, well, first, if there are any questions on anything we covered so far. And I hope that at least some of you are trying some of these things on your own. So if questions come up, you can ask us. But maybe what we can do now is to talk about module 2. And I think we can start there. And so here, once again, same story. These seem really wordy, but they're basically just doing very simple things, right? This is setting up the folder. This middle part here is setting up the folder for storing the results. We're setting these sort of housekeeping options for things like what should I call this thing? And in this case, we're going to call the model itself module 2A. And setting up the things about the parameters, the resolution of the files, and so on, right? Then in this case, we're back to, for speed purposes, we're back to a ratio image, a ratio model with a cylindrical surface. So this is like the way we were running module 1. So if you scroll down a little bit, this should all look very familiar. It doesn't have the 3 different options. It's just using one of the ways to read the files. And I guess you can go ahead and run this.
I need to start the other one.
Right.
Give me 1 second.
And you see what Ted is doing there to go to the running jobs and shut down specific, if you want to, or just to find out what the status is of jobs that are running. Depending on how good your CPU is, how many cores and so on, you could have multiple jobs running there and set them up and run and just go away and let them run.
Right, especially if you want to run the Smart RPDN model, you would need a computer. So in the Docker run command, you would have to allocate, I think it was 16 gigabytes. So some computers might not have that, but if you do have a computer that has that much RAM, that would be the preferred.
If you remember in the run command where I said CPUs equals 1, next to that it was saying memory equals 4 gigabytes. So you would have to change that to 16 if you're trying to learn these models.
Right. Yeah. Okay, so I will run module 2A right now. So I'll share my terminal again.
And so it's going to crank through and
So yeah, just setting up, validating, then getting all the right ones and then processing the images. So I think there's 10 images here in this module.
so this first step where it finds the cell and nuclear boundaries, that's common to all of the methods for cell shape. Because first you have to find the shape that you want to build a model of, and then you actually go ahead and construct the statistical shape model. All right, now if we go back to the notebook, it finished building the model. If you scroll down, right? No, go back to the notebook. Right, so it finished running, and then it ran SLML to info on the model that we just created. Okay, and that just prints out various fields from the model itself. Okay, now depending on what model it is and what options, what class and type of the model it is, it will it's telling you there whether or not it was able to use each of the images. So in this case, it was able to use them all, like they passed the criterion. And depending on what the model is, it may add other things to this info, like it might show you a shape space if it's a diffeomorphic model or a PCA model or a SFARM RPDM model. It will show you the shape space that it built for that particular example. All right. And so that's 2A. Maybe we can go to 2B. And in this case, what we're doing is, we're setting up options from the particular model to show us the shape space. Okay, so have you already run this one, or do you want to run it, Ted?
Yeah, I can run it again.
All right, so
Yeah, I can just run all of them.
there we go. So yeah, we can now that it's run. So what this does is it creates a folder called report in whatever directory you're working in, and inside of that is an index, an HTML file, and it has the same information we just talked about, but it will also generate various example images. So here it's generating a example shape evolution from the first cell to the second cell, right? It just does an illustration, and there are options that will let you set whatever cells it is that you want to display there. That's to illustrate that the synthesis of images in between. If we scroll up, what's happening here? That did not happen previously.
Hmm.
Do you need to maybe clear the directory and run it again?
Do you want to share yours quickly? Let me see if this is, let me see what the issue is.
I will run mine, and in the
Yeah.
meantime,
Let me see.
um, I've got to shut down my. I'm so I'm running 2B here. Hopefully you can see. So Sajin was asking a question. You got output. If you got output, it ran. Assuming, I mean, you can look at the log file and it will tell you whether there are any errors encountered. But then it will also produce the models. What we're showing now is examples of things we can do from the model once we've built it. In this case, we're using a model that was previously built. It's in the models folder, this model here, which is a model of a swarm RPD model for HeLa cells. We're, again, creating a folder to put the results in. Then we're running SLML to info on that model in order to create the various outputs that we're going to look at. Now, as I mentioned, my computer is a lot slower than Ted's. It's taking a little while to generate everything. In this case, what it's doing is, as we talked about, first doing this shape evolution. That means it has to synthesize a whole bunch of shapes, and then it's going to show the shape space, and then we're going to illustrate how we can change the shape space. Are you having any luck on yours, Ted?
Yeah, I needed to rebuild that container. So I'm still in the process of rebuilding it.
So it looks like mine is caught up.
Robert, sorry, can I ask another question? I apologize.
Sure thing.
Yeah, sorry about that, but I'm kind of, I don't know, maybe I'm kind of, I haven't used Docker. I was planning to, but I've never, well, anyway, in the Jupyter notebooks also. So I'm actually did everything that was followed up on the Google Doc, and the actual command that you showed there for Docker run to initiate the Jupyter notebook. I still cannot find the actual modules. I don't know why, and it's just empty directory. It shows me a local, and there's just a.
Once you've done that, you have to run the notebook download files?
I did download file, so I clicked on it. And what it does is just downloading something, and that's it. It's only 1.27 KB.
In your local file, in your local folder, there should now be all of those folders like in mine, right? So let's.
No, actually, I don't see them. That's the thing. I only see green.
Did you when you click on the download files, you then have to run it.
Okay, I click on download the files.
Then that opens up a notebook,
Yes.
and then you have to run the notebook.
Oh, okay, got it. I'm sorry. You see, I'm sorry. I've never.
That's okay.
I've
That's why
never run.
that's why
I've
we're
never
doing
run
this.
Jupyter notebooks. I've heard a lot about them, but so I click run, and
And
nothing happens.
it should start downloading. Okay.
Oh, it says retrieving, yeah, creating directory home of your local models.
So,
Okay.
by the way, in the meantime, my computer finished running module 2B. And what you see is the same shape evolution we were talking about before. And then it shows now a 3D shape space showing each of the cell and nuclear boundaries for the cells of this particular model. And then what we're going to do here is we're going to change the angle that we look at this. That's the view angle. And we're going to change the size of each of these cells. All right. So it's thinking again about it. So once we change those options and we run it again, and now it has to go and do it all over again. Now in this shape space plot, the cells will be shown larger, right? So the larger this number is, so before I think, yeah, so before we set to 800, that is smaller, so that this number is inverse. So what they're going to be now is 4 times larger, for visualizing the cells. Now, these are just for visualization. They are displayed at the point in the shape space that corresponds to their shape. Okay. If you want, you can turn off shape evolution, which is that plot that goes like this. I probably should have turned it off because it takes a while to generate that. You turn that off by just saying shape evolution is none. And as you see here, you can change how the shape space is viewed there. Okay, so that is what happens there. And what I think what we're going to do, we're not going to learn too much more from this. So what I think I'm going to do is shut this one down and go on to the next one, because yeah, let's do that. You've already seen the basic idea. We're going to get plots like that. We're just going to play with them to change, how it's displayed. All right. So I think you guys should still be able to see this. And we're going to go to running, and we're going to shut down 2B. Maybe first we'll open up this and see what we need. See if we need anything from. So what 2C is going to do is illustrate comparing two different models. Okay. In this case, we have two models that were run previously. And so we can show those by coming back here and going to
I have the container built. Do you want me to start sharing?
Oh,
again?
no, we don't need to rebuild it. It was running just fine. When I ran it, it ran just fine. Do you have Model 2A run completely?
Yes.
So you should have Model 2A and Model, let's see here.
Do you want me to share my screen?
Hold on a second. I need to do that. Do you have these files in your folder? In your model folder? Model 2A1 and Model 2A4?
Yes, I do.
Okay. So why don't you run Model 2C?
Okay. Do you want me to share my screen?
And then share your screen. I'll stop.
Okay, give me 1 moment. Nope, that's the wrong screen. That's the screen. So, okay, this is.
That's 2B. Notice how it increased the size of each of the cells, and now it's looking at it in only 2 dimensions by looking down the z-axis. And that's just displaying a different shape space model. So let's go to 2C. No, not the demos. There you go. So again, what this is doing, we're using SLML to report. If you look at the bottom of that screen, it says answer equals SLML to report. And what SLML to report takes is 2 models, model file 1, model file 2, and various options, just like we've been looking at. And what it's going to do then is create, if we scroll up a little bit, that's a joint shape space of those 2 models, right? One of them is blue and the other is cyan, okay? And that allows you to compare them, in this case, visually. Now, what you can also do, it's going to be in the next sub-release, is build a model of the probability distribution density of the cells and compare those. I talked about that today. That's not in this release. That'll be in 2.9.3. All right, so that's comparing 2 models via model to SLML to report. Okay. So let's go to, well, first I should stop, and you've been doing a lot of talking. Any questions about anything so far here? So there was a question about what module is for what. That's in the CellOrganizer document that's linked to the main page, right? Tutorial 1 is for reading files. Tutorial 2 is for constructing cell shape models. And module 3 is constructing protein organelle models. So that's what we're on right now. All right. So
excuse me, where I can find that? Sorry.
That's on the main workshop page. If you look at
In Google Doc or?
yeah, the cell modeling workshop Google Doc that has all the links and everything for all the sessions.
Oh, I see. I got it. Thank you. Sorry.
Okay,
Yeah.
and then next to this session, there should be a link.
Awesome. Yeah. Sorry for that. Yeah, I got it.
Okay.
Thank you. Thank you.
Sorry, I thought everybody was on that page. I should have pointed that out earlier. All
Thank you.
right. So where were we, Ted? So back to module 3 is about protein models. Okay. And so let's want to go ahead and run that one, Ted. And go ahead down. And what it will tell us is, again, information about the cells, the classes for cell shape and nuclear shape. And then it's saying that it also built a protein model at that downsampled resolution. And it lists which files it was successfully able to process. Okay, so that's for building protein models. And then this is again using SLML to report for comparing two protein models. Okay, so let's go ahead and run this guy. And I hope that you guys are able to at least get started on some of these so that you have some questions as we're going along. And I would encourage you, if you have the time, to try changing some of the options like we were talking about today, and find out more. All right, so in this case, what we're having here, SLML report, if what you're comparing are two protein models, then what it does is it compares the values of the parameters of the model. Okay, so in this case, one of the parameters of the model is the 3 of the parameters are the ellipsoid, width, length, and height, X, Y, and Z coordinates. And it's showing you the value of the coefficient of variation within the model for those two models for those parameters. So these are the parameters that are the most different between those two protein models. And the Z length is, quite a bit different in one of them than the other, varies a lot more. And if you scroll down, then it will also show the spatial distance, right? The probability density of where the organelles are relative to the cell and nuclear boundaries. So what this is saying is that the cyan model, there are no objects inside of the nucleus. That's the left side. there are objects in the cytoplasm, that's the right side, the distance being positive between the nucleus and the plasma membrane. And the cyan one are closer to the nucleus than the blue one. Okay, so that's another of the comparisons it's doing. So scroll up. And this is how many objects there are. This is over all of the images that it constructed the model of. What it observed was that the cyan model had fewer objects than the blue model. Okay, so that's using SLML report on protein models. Okay. Questions about any of that? So those were the things that we had wanted to cover. What I would, we can use the remaining time, maybe we can stay on and help people debug things if they're trying to get things running. Or if everybody's had a long day, we can stop here. Up to you guys.
I have a question. Actually, I'm still in module 1.
Okay.
And I tried to run it, but it seems that only the first box of the notebook is still running, and it takes more than 20 minutes. Is it normal?
So you look in your terminal window and see, or into the log file and see what it's saying, right?
My Windows, my machine is Windows, so I guess
okay.
that I'm not sure if it can show in the command.
Yeah, Ted, does the Windows version write to the log file? Okay, somebody is making a comment that the command, it shows it somewhere in the command line.
Yeah, I believe it should still output in whatever terminal you outputted.
Okay.
Whatever terminal you initiated the Docker run command. I personally do not have a Windows computer, so
You can also look in the log, see if you can open the log file.
So where can I find the log file?
Yeah, so if you go to that local folder, right? If you go to your desktop and into that MMBIOS 2021 folder, there you should find a folder called results.
Actually, for me, it's empty.
Then how are you able to run your notebooks if it's empty?
So maybe that's the problem. Maybe that's the reason that it takes for more than 20 minutes. So what I did, I just go to I type the Docker, the command that provided in instruction to the command line, and after that I downloaded the module and everything, so I could see my modules in the local folder, notebooks, workshop demos.
Okay,
and
good.
Then I just click on module 1, and there is a run icon that I just click on run.
Yes. Okay, run icon only runs one cell. It runs.
Oh, I see.
You want to run the whole note, it runs whatever your current cell is. If you want to run the whole notebook, you have to do cell run all under the cell model menu.
I find it. Okay, so okay, I got it. Thank you so much.
So that's what's happened is it's not doing anything because it just.
I see. That's why. Yeah, it was waiting for me. Okay, yeah. Thanks.
Yeah, I agree that that's just the weird thing about notebooks. that that doesn't run the whole thing, just runs the current cell.
Thank you so much.
Sure. other questions? What I'm going to suggest is that we take a little bit of, we have advanced topics tomorrow. That maybe at the beginning of that, we have stuff we want to do then, but maybe at the beginning of that, we can have sort of a quick Q&A or whatever. You know, if people have questions once we're done for today, maybe you can bring them up tomorrow. Right, you know, at the beginning of that session. But we're happy to hang on here and answer questions until this session is over.
Yeah, Robert, I'm kind of still having a little bit of issue with, so I run the actual notebook and I actually produce it kind of now showing that I have some models listed there within the notebook. I still do not see any modules. I don't know why, any images or anything. It's just kind of weird.
Depending on which model, which notebook you ran, if you ran notebook 1, all it should do is produce a model. Okay. If you run the module, the ones in module 2 and 3, those should produce some images that are the outputs of the reports.
I don't think I have actually run anything. I was able to actually got the Jupyter notebooks running.
Yeah.
Within the CellOrganizer, and then like you mentioned, once I clicked the actual download files link, when I clicked on it, it actually got me to the point of, I'm opening in a new tab actually. I'm using GUI, which kind of, you know, it's okay. But it's really slow. I don't know, maybe because I should have listened to your advice and just put one CPU. I think I kind of left a number of CPUs that were listed in the Google Doc, which were, I think, 4 or 2, something like that.
So Dima, maybe can I suggest that maybe you can go into a breakout room with Ted and maybe Ted can share with you.
Yeah, that would be great because I love that would be awesome. Yeah,
I don't know.
I really want to get this going for tomorrow before we start, because I have tons of images that I do want to analyze and be able to get some meaningful data out of it.
It looks like a breakout room has, well, why don't you guys go into breakout room 1, assuming you're able to.
Let's see. Yeah, I can do it. Can Ted go there?
Yep.
Cool.
Okay, great. Okay. So there was a question about modules 2 and 3. One of the things you can do is let me just get back here to my, do I have that shared? No. Is that you can look in the models folder. If you go into the models folder, models 3D, there are various models in there, especially in the Farm RPDM. Oh, I guess I didn't share it. Let me back up and share. So if we go into here and into models and into 3D and into Farm RPDM, those are the models that we were looking at before. Okay, so you can, and then there are other models in here which are not shapes models, but they're models for different organelles. And so, for example, you can compare, these are all different organelle models that are using that vesicle GMM, vesicle class type GMM. So you can do can run Model 2 SLML to report on pairs of these and see how they differ. And this is a diffeomorphic shape space. So you can run SLML to info on that. Here are various diffeomorphic models that you can run. And either visualize shape spaces of those or compare pairs of them, whatever you want. So that's some of the things I would suggest to do. And yeah. All right. And then what you can also do, and I'll share the changes to the notebook that we made to build this farm RPDM cell model. I will put that into Google Drive and share it with everybody. You can also download that. That's going to be this module 1B that Ted ran earlier. That is building a farm RPDM model. It takes a while, but that might be something you want, that you could run overnight to show how that works. Okay. Other questions or comments?
I have a question about the spherical harmonic in 3D.
Yeah.
So did you mention that the MATLAB code is also available?
Yes, absolutely. So if you go to CellOrganizer.org, here, let's go there. I'll share screen here in a minute. Is. So here's the main website for CellOrganizer, and under downloads, this is what we've been using. If you go there, then it will, it tells you here is the version that we've been running here. This is where we got it from, is from Docker Hub. You already have instructions for doing that, but here's the MATLAB version. Okay, so under download, CellOrganizer MATLAB 2.9.2, you have here 2 tarballs. Okay, this one has just the source code, and this has the images for testing. There is also a GitHub repository, but I would use this for right now because I don't know whether we pushed everything to the GitHub repository. I will check that by tomorrow with Ted to see whether or not the GitHub is up to date.
Thank you so much. Yeah, I think that I can, yeah. And one more question. So there is a paper that it's just recently published on bioRxiv from the Allen Institute that they use the spherical harmonic for the 3D shape.
Yes.
So this is the actual code for the paper, I think. Is it correct?
Yes.
Okay.
I think they have, this is the method. I think they may have another implementation, but I think that they're using the same code. Okay.
Cool. Thank you so much.
And by the way, there's all of the documentation is under this heading, right? There are lots and lots of documents there that describe, and so here's the documentation, for a lot of the stuff we've been talking about today.
Awesome. Thank you so much.
Sure. All right. Any other things? I think if there isn't anything else, I think I will see you all tomorrow at, let's see, at the first session tomorrow, right? At 10:30 Eastern, 7:30 Pacific.
Okay. Thank you. So do you mean that this session is finished?
I think, well, we can leave it open in case, you know, in case anybody has questions for Ted. I guess I can also, I mean, I can stay on, but we're basically done.
Okay, cool.
Unless there are any other issues that are coming up. And I guess that Tom has joined us. Hello, Tom.
I've been here listening in all along.
Oh, good.
Yeah.
So that's pretty much everything we wanted to cover today.
Great. Thank you very much.
All right, then I will say goodbye and see everybody tomorrow.
Okay, perfect. See you tomorrow.
Bye-bye.
Bye-bye. Thank you,
Ted.
everyone.
Thanks a lot, Ted. Thanks, Rosita.
Sure, thank you. Okay, see you tomorrow.
Okay.
Bye-bye.
Bye.